On this part of the video, we'll be looking at part 3 of paper 2. Part 3 of paper 2 is usually trigonometry. This is usually question number 5, 6, and 7 of paper 2. As an example, here we are looking at a Free State 2019 paper. We have a Cartesian plane with B located at the point when x is 3, y is minus 3 square root 3. We are required to find, without using a calculator, the value of OB. So for 5.1.1, we want to find OB. To find OB, we can either sketch a perpendicular line and use Pythagoras theorem to find OB. Where this side is 3 square root 3 and this side is equal to 3, so we can use Pythagoras theorem to find OB. But instead of using Pythagoras theorem, why not make use of analytical geometry in order to solve this problem? And using analytical geometry, we know that OB, to find OB, you just need the distance formed. We have 2 points, the point O, which is 0, 0, and point B, which is 3, and minus 3 square root 3. So we can find OB. OB is just the square root of 3 squared, which is 3 minus 0 all squared, plus negative 3 square root 3 all squared. And simplifying this, we're looking for the square root of 9 plus 3 times 9, which is equal to the square root of 9 times 3 is 27, 27 plus 9 is 36, so this is equal to 6. So OB is equal to 6 units. And for 5.1.2, we are required to find cos alpha plus theta. Alpha plus 30 degrees. Now to find cos alpha plus 30 degrees, we first need to find alpha. We can find alpha by extending our line. If we extend the line, we have the angle theta. These are vertically opposite angles, so they should both be theta. So we can use, to find theta, we need to find the gradients of this line. So we need to find the gradients of OB. The gradients of OB, by definition, is equal to change in y over change in x. So it's change in y minus 3 square root 3 divided by change in x, which is 3. And this is just negative square root 3. So your change in y over change in x is equal to negative square root 3, which is the gradients of this line. By definition, the gradients OB is equal to tan of theta. So the gradient OB can be found by finding tan of theta, and this is equal to minus square root 3. Therefore, theta should be equal to arctan of negative square root 3. To find arctan of negative square root 3, we need to sketch the 30, 60 triangle. With the 30, 60 triangle, we have 1, we have half, we have square root 3 over 2. The long side is half the short side. So theta so we have tan is y divided by x. So theta should be equal to 60 degrees. So the negative, so it should be negative 60 degrees. So theta is equal to negative 60 degrees. It is red, anti-clockwise. If we're moving clockwise, then we get this line. So theta is negative 30 degrees if we're moving clockwise. If we're moving anti-clockwise, then theta must be equal to alpha, which is equal to 360 minus this 60, which is 300. So alpha is equal to 300. So if you want to find cos alpha plus 30, that will either be cos of 300 plus 30, or we can use this negative 60 plus 30. So this is equal to cos negative 60 plus 30, or 300 plus 30. They are one and the same thing. This is when we're reading the angle clockwise, and alpha is when we read the angle anti-clockwise. So you could write 300 plus 30, which is 330, and 330 minus 360 degrees will return you back to where you're coming from to get the same thing. So this is cos of negative 30, which is just cos 30, and cos 30, you can read that from our triangle. Cos 30 is x divided by r, so it is square root 3 over 2 divided by 1, which is just square root 3 over 2. And for number 5.2, we are required to simplify sine squared 90 minus x, tan 360 minus x, divided by sine of minus x. So for 5.2, are required to simplify sine squared of 90 minus x tan of 360 minus x divided by sine of minus x. This can be written as cos squared x. Sine of 90 minus x is cos x. And here we have tan of 360 minus x. We go to the fourth quadrant where tan is negative, so this should be equal to negative tan of x divided by negative sine of x. The negatives will cancel out, so we can just cancel out these negatives. And write this as cos squared x times your tan x is equal to sine x divided by cos x. And this is all over sine x. We can cancel out the cos x. If we cancel out the cos x, we get cos x sine x divided by sine x. Again, we can cancel out the sine x to get cos x. For number 5.3, we want to prove that cos 60 plus theta minus cos 60 minus theta is equal to negative square root 3 sine theta. So we are required to prove that cos of 60 plus theta minus cos of 60 minus theta is equal to minus square root 3 sine theta. So what we want to do is we want to take the more complicated function, simplify it, and see if it's exactly the same as the right hand side. So we let on our left hand side, look at the left hand side, we have cos 60 plus theta minus cos 60 minus theta. this is equal to cos 60 cos theta minus sine 60 sine theta minus cos 60 cos theta plus sine 60 sine theta. These two terms are the same, so they should cancel out. And if we multiply this by negative, positive will change to a negative, so we can just add these two. So we have negative 2 sine 60 sine theta. We need to simplify sine theta. So we have the 60, 30 triangle, 1/2 square root 3 over 2. So sine 60 is equal to y divided by r. Sine 60 is y divided by r, which is equal to square root 3 over 2 sine theta. And simplifying, we have negative square root 3 sine theta. So we want to check if this is exactly the same as the right hand side. On the right hand side, we have negative square root 3 sine theta. So this is equal to the right hand side, which proves our identity. And for number 5.4, we'll consider the following identity, which is 1 minus sine 2a divided by sine a minus cos a is equal to sine a minus cos a. And for 5.4.1, we are required to prove the identity. And for 5.4.2, it's for which values of a in the interval between 0 and 180 will the identity be undefined. So when will this identity be undefined? It will be undefined when this value is equal to 0. So let's start by proving the identity. So we look at 5.4.1. we have 1 minus sine 2a divided by sine a minus cos a. And we want to show that this is equal to sine a minus cos a. 1 minus sine 2a divided by sine a minus cos a is equal to sine a minus cos a. So on the left hand side, we have 1 minus sine 2a divided by sine a minus cos a. So what we want to do is we want to simplify this sum using double angles. We have 1 minus 2 sine a cos a divided by sine a minus cos a. We have 1 minus 2 sine a cos a divided by sine a minus cos a. Now what I want to do is I want to get rid of this one. I know that sine squared plus cos squared is equal to 1. So what I'll do is I'll replace the 1 with sine squared plus cos squared to get sine squared a plus cos squared a minus 2 sine a cos a divided by sine a minus cos a. And we can factorize the numerator to get sine a minus cos a multiplied by sine a minus cos a divided by sine a minus cos a. And these two terms will cancel out, do the same. So here we can write this as sine a minus cos a. We need to check if this is equal to the right hand side. And on the right hand side, we have sine a minus cos a. So this is indeed equal to the right hand side, which proves our identity. And the second part was to find the values for which the identity will be undefined. And those values will when the denominator is equal to 0. This will be undefined when the denominator is 0. That is when sine a minus cos a is equal to 0. So for number 5.4.2, our identity would be undefined when sine a minus cos a is equal to 0. This is when sine A is equal to cos A. If we divide both sides by cos A, we get sine A divided by cos A is equal to 1. Now sine A divided by cos A is tan A. So we have tan A equal to 1. And this is 1 when A is equal to arctan of 1. And this is clearly from the 45 triangle. So here we have y, if this is our theta, so we have y divided by x is equal to 1. Therefore, theta must be equal to, or A must be equal to 45 degrees. If A is equal to 45 degrees, the identity would be undefined for theta between 0 and 180 degrees. For question number 6, we are required to find the general solution the general solution of sine 2x equals cos x minus theta. So we want to find the general solution. We want the general solution for sine of 2x equals cos of x minus theta. To solve this equation, we want the left hand side to be the same as the right hand side. To do that, we can write the left hand side as cos of 2x minus 90. That is equal to cos of x minus theta. Change the left. On the left we have cos, on the right we have cos. For these two to be the same, the inside must be the same. That is 2x minus 90 must be equal to x minus theta. Which implies the 2x minus x must be equal to 90 minus theta plus the period of cos theta, which is 360 k, where k is an element of an integer. So x must be equal to 60 plus 360k. We can also change the right hand side to sine. So we have sine sine of 2x is equal to sine of 90 minus x minus 30. We should change cos on the right hand side to sine. Again, here we have sine. Since we have sine on the left and sine on the right, the inside must be the same. That is 2x must be equal to 90 minus x plus 30. And 3x must be equal to 120. And the period of sine is again 260 k, where k is an unit of an integer. Therefore, x is equal to 40 plus 120 k is another solution. So this equation has two periodic solutions, where the first general solution is x equal to 60 plus 360k, and the second general solution is x equal to 40 plus 120k, where this solution has period 120 and this solution has period 360. Now for 6.2, where diagram below given with g of x equals cos x minus 30 for the interval minus 180 to 180. We are required to write down the period of g. G is cos x minus 30. It is exactly the same as cos x, but shifted 30 units to the right. So its period should be equal to 360. So the period should be 360 degrees. Determine the values of x for which the graph of g is increasing. So we want to find the values for which the graph is increasing. Clearly, the graph is increasing in this interval. So we can clearly see it is increasing in this interval and it is decreasing in this interval. It is increasing in this interval and decreasing in this interval. So it is increasing from 150 to 30. It is increasing from 150 to 30. So the interval where the graph is increasing, it is increasing for the values of x between minus 150 less than 30 degrees. We have to exclude the lower and the upper bound, since at 150 our function is stationary, and at 30 our function is stationary. It is neither increasing nor decreasing. For 6.3, on the same system of x's, we want to draw the graph of f of x equals sine 2x. We want to draw the graph of f of x equals sine 2x. What sine 2x does is just decreases the period of sine x. So let's plot points. When x is 0, y is 0. When x is 90, y should be 0. And when x is 180, y should be 0. We do the same thing on the left hand side. So we are at 0, at 90, minus 90, and we're at 0, at 180. Since our period is decreased from 360 to 180, so here f of x would be 1 at 90 divided by 2, which is 45. So this is 15, this is 30, 45. At 45, our function should be 1. So we're counting 1, 2, 3 lines. And at 135, we should be at minus 1. Similarly, on the left, at negative 45, we should be at minus 1. And at negative 135, we should be at 1. And joining the dots, we have the graph of sine 2x. And for number 6.4, we're required to find the interval for which f times g is less than 0. F times g would be less than 0 if f and g have different signs. That is, if either f is negative, if f is negative, g must be positive. If g is negative, f must be positive. So you have f and g being less than 0. So here, from 180 to 90, clearly f is positive. It's above 0. It is positive. And for the same values between minus 180 to 90, you can clearly see that G is negative. So f times G f of x times G of x is less than 0 whenever x lies between 180 and 90. For x lying between negative 180 and 90, you can clearly see that f times G is negative. Between 90 and 60, both f and g are negative. Therefore, f times g should be positive. From 60 to 0, from 60 to 0, f and g have different signs. From x equal to minus 60 to x equal to 0, they both have different signs. Therefore, f times g is negative. Note that at the endpoint here at 180, I've excluded negative 180 because here this function is 0. Anything times 0 is 0. 0 is neither positive nor negative. So I have to exclude the minus 180. Same goes with 90. At 90, the yellow line is 0. Anything times 0 is 0. And here both are positive, so f times g is positive. And just after 90, you can clearly see that the yellow line is negative and the black line is positive. So from from 90 all the way to 120. 90 to 120, you can clearly see that this line is negative and this line is positive. Therefore, the product should be negative. And that was 6.2.4. And for number 7, we have a diagram. B, C, D are 3 points on the same horizontal plane, such that BD is equal to DC, which is equal to 1. DCB, DBC is equal to alpha, and ABD is equal to theta. Then BC is equal to x. We are required to prove that AB is equal to x divided by 2 cos alpha cos theta. AB is equal to x divided by 2 cos alpha cos theta. So here we want to use x, and we also want to use alpha, and we want to use these. So the best way of using all these values is maybe using the fact that a over sine a is equal to b over sine b. A over sine a is equal to b over sine b. So if this is alpha, since these two are the same, then this angle should also be equal to alpha. If this angle is alpha, then d should be equal to 180 minus alpha. D should be equal to 180 minus alpha. So y divided by sine alpha is equal to x divided by sine of 180 minus alpha. And this implies that y is equal to x sine alpha divided by sine of 180 minus alpha. But this BD is also equal to y. BD is equal to y. This is a right angle triangle. So AB so we have cos we have cos theta is equal to adjacent divided by hypotenuse. Adjacent divided by hypotenuse, which is AP. Where y So here we should have minus 12. Where y is equal to x sine alpha divided by sine 180 divided by 12. So we have a b cos theta is equal to x sine alpha divided by sine of 180 minus 12. So simplifying, we have AB is equal to x sine alpha divided by cos theta multiplied by sine of 2 times 90 minus of. And this is equal to x sine alpha divided by cos theta multiplied by 2 sine 90 minus alpha multiplied by cos 90 minus alpha, which is equal to x sine alpha divided by cos theta, take the 2 out, and sine 90 minus alpha is equal to cos alpha, and cos 90 minus alpha is equal to sine alpha, which is equal to, so this will cancel out, so we have x divided by 2 cos theta cos alpha, proving the statement. On this part of the video, we'll be looking at question number 8, 9, and 10 of paper 2, which is Euclidean geometry. As an example, we'll start off with the 2020 KZN paper. In the diagram, we have SBT, we have SA, and we have TC, which are tangents to the circle at B, A, and C. We have AB produced to P, we have AC produced to Q, and we have T lying on PQ. And we are given triangle APQ with AB over AP being equal to AC over AQ. And we want to prove the following information. At this point in time, you may want to stop, look at the diagram and the given information. Now, to prove angle A2 is equal to angle T1, we may want to let A2 equal to X. Now, think about any other angles in the given diagram that are equal to X. Pause and think about any other angles in the diagram that are equal to X with reason. Now, look at tangent SB. You can clearly see that using tangent SB, B3 must be equal to X. B3 must be equal to X, and the reason being tan chord theorem. By tan chord theorem, A2 is equal to B3. We can also use tangent TC. Look at tangent TC. C2 must be equal to X. C2 is equal to X using tangent TC. Again, this is because of tan chord theorem. Now, is there any other angle that is equal to X? Pause for a second and think about it. Now, look at the given information. We are given that in triangle APQ, AB over AP is equal to AC over AQ. But this is a proportional theorem. So it's actually the converse of, by the converse of a proportional theorem, BC must be parallel to PQ, given this information. So BC must be parallel to PQ. BC must be parallel to PQ. So if BC is parallel to PQ, then we can find other angles that are equal to X. Now look at C2 and T1. These are alternating angles. Since BC is parallel to PQ, C2 must be equal to T1, which is equal to X. For the same reason, these are alternating angles. T3 should also be equal to X. B3 and C3 are alternating angles. So we have 1, 2, 3, 4, 5 angles that are equal to X. That are the same. These angles are the same. Since all these angles are the same, you can clearly see that A2 must be equal to T1. Let's write this information down. So for number 8.2.1, we are required to prove that A2 is equal to T1. Note that here tangent TC and TB meet at point T, at a common point. Since these two meet at a common point, then these two lines must be the same. These two lines are the same since they meet at the common point. Tangents from the common point, and the common point is C. If these two are the same, clearly the angles in the base are the same. And we can clearly see that we have x here and x there, they're the same. So TC is equal to TB, tangent from the same chord. Now going back to question number 8.2.1, we are required to show proof that A2 is equal to T1. So we started off with A2, so the angle A2 is equal to, you can choose any one that we spoke about. We can just quickly go to this one and say A2 is equal to C2, and the reason for A2 being equal to C2 we said was sun chord theorem. And we may want to write down which tangent we are actually talking about. We're talking about tangent TC. So A2 is equal to C2, and we said since AB over AP is equal to AC over AQ, which is given. Then BC is parallel to PQ. And this is a proportional theorem. By proportional theorem, or the converse of proportional theorem, this must be parallel. Now, because these are parallel, we therefore have angle C3, C2 is equal to angle T1, angle C2 is equal to angle T1, and these are alternating angles. With BC parallel to PQ. If A2 is equal to C2 and C2 is equal to T1, then A2 must be equal to T1. Hence, A2 is equal to angle T1, which proves the statement number 1. And for 8.2.2, we want to prove that triangle ABC is similar to triangle TCQ. So we want to prove that these two are similar triangles. To prove that these two are similar triangles, you can just prove that all the angles are the same. All the angles are equal. If all the angles are equal, then these two must be similar. We can start off with the given information. Clearly, this has been proven, and it is equal between these two triangles. So we can use that information. So we have A2 equal to T1, and that has been proven. So we just need to find one more angle in TCQ that is equal to an angle in ABC. So we just need to find one more angle. So the best guess to work with would be C1. Now look at C1. Which other angle is equal to C1? Pause and think about it. C4. C4 is equal to C1. These are vertically opposite. Let's call it Y. If we call C1 Y, then C4 must be Y, since they are vertically opposite. Which other angle is equal to C4? We can use this tangent, TC. Using TC, you can clearly see that angle B2 must be equal to Y. Again, this is because of tan chord theorem. Is there any other angle that is equal to Y? Yes, there is. Recall that BC is parallel to PQ. Therefore, P is also equal to Y. They are corresponding angles. These are corresponding angles. Therefore, P should also be equal to Y. So P is also equal to Y. So these two are parallel. Now let's go back to what we wanted to prove. We're trying to prove that triangle ABC is similar to triangle TCQ. We have this angle in C. We have this angle in this triangle, which is equal to this angle in this triangle. And we have this angle in this triangle, which is equal to this angle in this triangle. Therefore, clearly these two are similar, because the other angle must be the same as the sum of triangles add up to 180 degrees. So this must be the same. Besides, these are parallel and these are corresponding. We could have just used the fact that these are corresponding angles, therefore they are the same. So we can either say these are corresponding angles, therefore they are the same, or since we have two that are the same, therefore this must be the same, since the sum of the triangles must add up to 180 degrees. Any of those reasons should suffice. Let's go ahead and write our solution. So we said A2 is equal to T1, and that was proven. And we said C1 is equal to C4. C1 is equal to C4, and those were vertically opposite angles. and we said C4 is equal to B2 and that was because of time chord theorem. Where we used tangent TC. Tangent TC was used, just to be sure. And we said Q is equal to C3. So Q is equal to C3 either because of sum of a triangle, some angles of a triangle, or corresponding angles. Corresponding angles with using BC parallel to PQ. BC parallel to PQ. So we can either use this statement or this statement. So we have all the angles are equal. Therefore, the triangles must be similar. Therefore, a triangle ABC must be similar to triangle TCQ. So we have proven that these two are similar. And now we want to prove that ABTQ is a cyclic quad. ABTQ is a cyclic quad. Pause and think about it. How do we prove that this is a cyclic quad? To prove that this is a cyclic quad, we can either prove that the supplementary angles add up to 180 degrees. If we add these angles, we should get 180 degrees. Or if we add these angles, we should get 180 degrees. Then we have proven that this is a cyclic quad. But much easier would be using exterior angle of a cyclic quad. With an exterior angle of a cyclic quad, what we want to prove is that this angle is equal to Q, or we can prove that this angle T3 is equal to A. And I think we have already done that. It's a matter of just writing it down. We have already shown that T3 is equal to A3, therefore this is a cyclic quad. So it's a matter of just writing down the information for the exam. So we look at 8.2.3. 8.2.3, we're proving a cyclic quad. So we said, how did we get here? We said if A2 is X, B3 is equal to X. Have we written anything down? Have we written down the fact that A2 is equal to B3? Nope, we have not. So we can write it down. So we have A2 is equal to B3. Had we written it down somewhere here, we would have just said proven, but we have not written it down, so we need to state why these are the same. So we said they are the same because of Tan-Quad theorem. Which tangent? We are using tan ST or SPT. So this is equal to this, and the B3 is equal to T3. And these are alternating angles. Which lines did we use? We used this line BC parallel to PQ. BC parallel to PQ. And we are done. We just need a conclusion. Therefore, ABTQ ABTQ is a cyclic quad. Reason? Exterior angles of a cyclic quad. Exterior angles equals interior angles of a cyclic quad. So we have proven 8.3.2. We now want to prove that TQ is tangent to the circle TPC. So if we have a circle at TPC, so if we have a circle at TPC, excuse my drawing. So if we have a circle at TPC, we want to show that PQ is a tangent to that circle at T. Now, since we're dealing with a triangle inscribed inside a circle, all we want to do is we wanna use a Tan-Quad theorem to prove this. So we basically want to show, if we can show that this T1 is equal to B3, we are done. I'm not sure why we have so many marks, but it should be that simple. If we just show that T3 is equal to B3, which we have already done, then we are done with it. It's a matter of just writing this down. Or we can show that T3 is equal to C2. If you can show that C3 is equal to C2, we are also done. And that has been done as well. So it's a matter of just writing the reasoning down. So we are done. So let's go for 8.8.2.4. We want to prove that TQ is a tangent. Now, what have we written down? We've written down that B3 is equal to C3. B3 is equal to C3. That has been written down in discussion, so we can use it. So it's B3 is equal to C3. B3 is equal to C3, and that has been proven above. Okay, we can use that. We have proven in 8.3 that B3 is equal to C3. Or you can use alt angles, is still the same thing. So that has been proven, and we have not shown that these two are the same. You can just say that TB is equal to TC. TB is equal to TC. And this is because of time from common point. We spoke about this last time, that these two tangents are from a common point T. Therefore, these two lines are the same. Therefore, these two are the same. Therefore, B3 is equal to B2. Therefore, B3 is equal to, B3 is equal to C2. And you can just see association. Or simply because T. And this is a reason TB equal to TC, therefore these two are the same. It's an isosceles triangle. And if B3 is equal to C3 and B3 is equal to C2, therefore C3 is equal to C3 is equal to C2. We just wrote it down, but we have not shown the reasoning to the exam. Therefore, C3 is equal to C2. If C3 is equal to C2, then TQ must be a tangent. Two triangles, to circle TBC. And the reason for that is tan chord theorem. And we are done. tan quad theorem. And this example is taken from the Department of Education's 2010 exam paper. This was the 2010 exam paper. Now, for this example, diagram below, we have two circles having common tangents, and we have PT, which is a tangent to the smaller circle. We have PAQ, and QRT, and NAR, which are straight line. We're given that Q is equal to X, and we are required to find with reason 3 other angles that are equal to X. So we can pause and think about this and try and find 3 other angles that are equal to X. Now, if this is X and TB is a tangent, since TB is a tangent to circle ARQ, then T2 must be equal to X. T2 must be equal to X. This is tan because of tan quad theorem. I'll use tan quad theorem. By tan quad theorem, A2 must be equal to X. Now look at this line, TB, and this line, AN. Because these are straight lines, then A5 must also be equal to X. These are vertically opposite angles. This should be equal to X. They are vertically opposite angles. And I can use this tangent on the smaller circle. Using the tangent on the smaller circle, you can clearly see that A5 is equal to P2, tan quad theorem. So P2 must be equal to X. We have 1, we have 2, we have 3 angles that are equal to X. So it's a matter of just writing them down. So for 9.1.1, we said A2 is equal to X, and the reason was tan quad theorem. Which a tangent to using term TB on circle, just to be sure. ARQ. It says tan quad theorem. This is the most important part. And we said A5 is equal to X, and this was because of vertically opposite angles. We used vertically opposite angles, and they said this is also equal to x. And they said a p2 is equal to x. P2 is equal to x. Here we use sine cot theorem. Which are tangents. Again, we are using tangents TB. On circle PNA. So we have the three angles that are equal to x. Now we want to prove that APQR is a cyclic quad. APTR. So we want to prove that this is a cyclic quad. Again, also prove this is a cyclic quad. If we are not given angles, we may just want to use exterior angle of a cyclic quad. So here we're looking for exteriors of this cyclic quad that are nice or easy to work with. You may want to work with this, but here I have P2 and P1. So what I want to do is I want to show that this is equal to this. If I can show that this is equal to this, I'm done. It's a cyclic quad due to exterior angle of a cyclic quad. Or I can just show that this is equal to that angle. Again, sorry, not this. We're looking at this cyclic quad, so we want to show that A4 is equal to this 2. A4 is equal to this 2 exterior angle of a cyclic quad. Or we can just show that this R2 is equal to P1, again exterior angles of a cyclic quad. I think it would be much easier to show this because we're just dealing with one angle. Let's do this one. So we want to show R2 is equal to P1. Let's call R2Y. Let's call this Y. So if R2 is Y, we can look at this sun. So with this tangent, it must be equal to, R2 must be equal to A6 tan cot theorem. So it's equal to A6 tan cot theorem. Because of tan cot theorem, these two are the same. Again, these lines are straight. We have vertically opposite angles. So A3 must be equal to Y. And here we can use this tangent and tan cot theorem. With tan cot theorem, this must be equal to this. So n must be equal to y. We're using this tangent. Tan cot theorem states that this angle A3 must be equal to n. We also have this tangent on the smaller circle. By tan cot theorem, these two must be the same. So this should also be equal to. We are done. So this is y, and this is y, and this is y, and this is y. So this is equal to this. So this is a cyclic quad. So we just need to write it down for the exam.
For number 9.1.2, we said R1 is equal to A6. Angle R1 is R1 or R2. Angle R2 is equal to angle A6, and that was because of tan chord theorem. So we'll just write tan chord theorem. At tan chord theorem, I'm using this tangent. We said A3 is equal to A6 is equal to A3. And these are vertically opposite angles. Therefore, R2 must be equal to A3. Or you can just say let R2 equal to X and go with the flow. Or Y, sorry. And they said N is equal to A3. And this was tan chord theorem on the smaller circle. Which implies that N is equal to R2. And I said N is equal to P1. Again, we are just playing around tan chord theorem. Maybe we should state which tangent we are talking about. Otherwise, it should be just tan chord theorem throughout. Therefore, R2 is equal to P1, which is what we are looking for. If R2 is equal to P1, then this is a cyclic chord. Therefore, APTR is a cyclic chord. APTR is a cyclic chord. Resin exterior angles of a cyclic chord. Exterior angles of a cyclic chord. Now, this example is taken from a Gauteng 2020 trial exam. It's question number 8 of the exam. In the diagram below, we have point A, B, C, D. Point A, B, C, D, which lie in the circumference of a circle with AB parallel to EC. CB is produced to E. GD is the tangent to the circle. Oh, GD is a tangent. And BD is equal to AD. BD is equal to AD. We want to calculate with reason the size of the following angles. So with reason, we want to find the size of ADC. So we want to find the size of ADC with reason. Given that B1 is equal to 67, D1, sorry, this angle D2 plus D3 should also be equal to 67. Exterior angle of a cyclic quad. So this ADC should be equal to 67 degrees. This is exterior angles of a cyclic quad. These are exterior angles of a cyclic quad. Want to find the size of C. So let's write down the value there. You said this is 67 degrees. And we want to find the value of C. C now these two are parallel. If these two are parallel, then these must be co-interior angles. If these are co-interior angles, they should add up to 180 degrees. So we just take 180. So this angle would be 180 minus 67. So C2 is equal to 180 degrees minus 67 degrees. The reason being co-interior angles. They are co-interior angles, so they should be 180 minus 67. You should get 113 degrees. 113 degrees. And for angle A, angle A should be 67 degrees. You can just use these are supplementary angles. they should add up to 180 degrees. C and A are supplementary, they should add up to 180. So I'm just adding this value back. (113) plus 67 is equal to 180. So this must be 67. Or you can just say EC and AC are parallel. These two are parallel, and this must be alt angles. Since they are alternating angles, this must be equal to 67 degrees. Alternating angles. So you can either use supplementary angles or alternating angles. So A is equal to 67 degrees, reason being it's alternating angles if we are using these two parallel lines, BC parallel to AD. Or you can use supplementary angles. You can use supplementary angles. Now for D2, for D2, okay, we have this as 67. These two sides are the same. We are given these two sides are the same. AD equals to BD are the same. So B2 should be equal to 67 as well. If B2 is equal to 67 and A2 is equal to 67, then D2 must be equal to 67, 180 minus 67 times 2. 180 minus 67 degrees minus 67 degrees. Or 180 minus 67 times 2. This is an isosceles triangle. Or just you can just say BD equal to 18. Should be fine. So we have 180 minus so this should be equal to 46 degrees. So D2 is equal to 46 degrees. Now look at BDG. BDG is, recall that we said this is 113 degrees. So BDG should also be equal to 113 degrees, because this is Tanko theorem. By Tanko theorem, these two should be the same. As DG is a tangent, is it not? Yeah, it's a tangent. So BDG is equal to 113, and that is because of Tanko theorem. By Tanko theorem, they should be equal to 113 degrees. prove that AB is equal to CD. Where is AB? AB and CD. We want to prove that these two are the same. So for BD, AB, we said this angle was 46. We said this angle is equal to 46 degrees. D2, so D2 is equal to 46 degrees. All you need to do is, let me just show that B3, if you can show that B3 is equal to 46 degrees, then we're done. Okay, this is 67 degrees and this is 67 degrees. So we have B3 let me just check if we've worked out B3. No. B3 is equal to 180 minus 67 minus 67. It's 180 degrees. It's a straight line. We have a straight line CBD. So it is 180 degrees minus this 67 minus this 67. We should get B3, which is equal to, it's the same as this value, which is equal to 46 degrees. So B3 is equal to, we have B3 is the same as D2. Since B3 and D2 are the same, we have this triangle as 46 degrees at the circumference with chord BA, and this triangle has 46 degrees at the circumference with a chord CB. Therefore, these two must be the same. AB must be equal to CD. AB equal to CD, and the reason is that they have is the converse of angles with the same chord, or segments. So these we'll see angles subtended by same equal segments chord. So they are subtended by equal chords. They are equal, not common but equal. So it's actually the converse of this chord, of this theorem. So we are done. As an exercise, you may want to have a look at this problem. With this problem, we're trying to find with reason three angles that are equal to M. This is where I'll stop. Thank you for attending the session.